Миша, слышно нас?
Hello. Yes. Thank you for invitation and for possibility to give a talk at such a beautiful conference. The goal of my talk to report on recent joint research of Leonid Chekhov and me. And I will try to explain all this symplectic groupoid thing, log-canonical coordinates, and so on. So basically, the main goal is to establish a connection between two Poisson varieties. First of all, first one is a symplectic groupoid of unipotent upper triangular, well, generally speaking, n by n matrices equipped with natural Poisson bracket, which goes back to works by Alan Weinstein, Dubrovin Ugagle, and was studied in great detail by Bondel. And second object is Teichmüller space of closed Riemann surfaces of some genus. In particular, we will concentrate on 3x3 matrices and genus 2 closed Riemann surfaces when this picture is especially nice. Well, first object is basically just unipotent 3x3 matrices, so it's three-dimensional space. Well, I will explain that it has kind of natural Poisson bracket. The second object is kind of very well-known Teichmüller space. And log-canonical coordinates means some coordinates which behave especially nicely with respect to this Poisson bracket. So Poisson bracket takes very nice form if written in these coordinates. Again, I will explain further what does it exactly means. So kind of main observation is the following, that one can ask the following question. So Teichmüller space is equipped with famous Goldman Poisson bracket. And well, one can ask the question, what are the nicest coordinates for this Goldman Poisson bracket on Teichmüller space? Such coordinates are very well known if our surface has boundaries, like if it's some genus, if topologically we consider Teichmüller space of genus G surfaces with S holes, where S is greater or equal than 1. But surprisingly, such well, they are called shear coordinates, and they were introduced by Thurston, Father Thurston, well, in 80s, I guess. But surprisingly, such coordinates are not known if there are no holes. The reason is that if there is holes, one can look at triangulation, like ideal triangulation of the surface, and you know the holes play the role of vertices of this triangulation. So if we don't have holes, we don't have vertices, we don't know what to start with. So it's kind of the stupid reason really breaks the whole construction, and such coordinates, to the best of our knowledge, was not known until recently. And as a byproduct of our project, we obtained such nice coordinates for specifically for Teichmüller space of genus 2 closed surfaces, and hopefully we can say something about higher genera, but it's a work in progress, and I probably won't be able to touch it here. Any questions? Is kind of main message, is it clear? Okay. If yes, so let me start with explaining what is symplectic groupoid and what is this nice Poisson structure to symplectic groupoid. So let's introduce the following notation. This well, this AN, well, denoted such, is the space of unipotent upper triangular n by n real matrices. So like that. And by symplectic groupoid Mn, we will denote the pair of two matrices, B and A, where B is just the usual square n by n matrix, non-degenerate one, and A is this unipotent upper triangular matrix with one extra condition. So if you consider BA-B transpose, then it will also be unipotent upper triangular. So this is kind of important condition which define as symplectic groupoid. Alan Weinstein in 87 introduced a natural symplectic structure on similar objects, like in more general situations. And the main properties of this symplectic structure is the following. So it's basically determined almost uniquely up to proportionality by the following universal property. Let's consider M being a set of all such compatible pairs, like this symplectic groupoid. And by M2, we will denote its fiber product, namely the set of pairs BA and C BA-B transpose. So kind of, well, the unipotent upper triangular matrix in the second pair is sort of the result of, well, this operation can be, sorry, probably I will just call it back. So in this construction, when we consider symplectic groupoid, this unipotent upper triangular matrix, one can consider as an object, and it's a sort of triangular form, and B is sort of morphism. We checked on this triangular form whenever it's possible. So here, the object of the second pair is the result of applying of our morphism B to the object A. So this fiber product is constructed in such way that one can do concatenation. So one can apply B to A, and then to the result, one can apply C. So this naturally define this product map M from M2 to M. So if we take such a pair, we consider its product, and it's just a pair A and CB. And then one also M2 has two natural projections on M. So P1 just takes the pair the CBA-B transpose, and second BA to CBA-B transpose, and P2 take it to BA. Then theorem by Weinstein claims that there exists a unique up to proportionality symplectic structure omega on M such that pushback by map M of omega is equal to the sum of pushback P. It should be P. Sorry, my mistake. Pushback by omega by P1 plus pushback of omega by P2. And as I said, so this symplectic structure is unique up to scalar coefficient. Okay, now.
Sorry, Misha. Unique in which sense?
Say it again.
In which sense is the symplectic structure unique?
I mean, if you have symplectic structure on M which satisfies this condition, then you can just multiply it by scalar. It's up to scalar multiplication by scalar. It's unique symplectic structure which satisfies this condition. Okay.
Okay. Yeah.
Okay. So, well, now we will use this symplectic structure to induce some Poisson structure on the upper triangular on unipotent upper triangular matrices in the following way. So let's take this the set of pairs, our symplectic groupoid, and we have well, it contains it is coincide with the set of all pairs BA compatible pairs. Now we can do two projection again from this set to set of unipotent upper triangular matrices. First projection S takes pair BA to A, and second projection T takes pair BA to BA-B transpose. And in particular, so one can take M is equipped with symplectic structure, one can take dual Poisson structure, and then push forward it along S to this unipotent upper triangular matrices. It defines as, well, kind of Poisson structure on the set of unipotent upper triangular matrices. And this structure was studied, kind of discovered many times by physicists first, and then it was studied in great details rediscovered by Dubrovin and Ugagle, and then it was studied in great detail by Bondal in 80s and in some preprint, which was published as a paper like in 2000. So one fact about this structure is that its core rank is integer part of n over 2. So core rank is determined by the number of Casimir functions. And here Casimir's function are given by the following. So we can, if we have matrix A, this unipotent upper triangular matrix, we can consider matrix A plus lambda A transpose, take its determinant. We will get some degree n polynomial, which is palindromic. So the first coefficient coincide with the last one, and so on. Second with n minus, kind of the first before the last one, and so on. So there is exactly this number of independent coefficients of this palindromic polynomial. And they form the basis for the set of Casimir function on this form of this Poisson structure. Okay. Now now our goal is to look for some nice coordinates with respect to this Poisson structure. So let's introduce the following definition. We say that a collection of functions f1, fn on a Poisson variety x equipped with a Poisson bracket is log-canonical if Poisson bracket between two functions fi and fj, any pair of functions fi and fj from this collection is just a constant times the product fi times fj. So another way to think about that, if you take the Poisson bracket between log fi and log fj, you will just get a constant. So it's sort of, well, this property is kind of can be rewritten as saying that Poisson bracket between logs is just constant Poisson bracket. And we will try to kind of find nice coordinates. And well, remark is that there is theory of cluster algebra, which says that if such coordinates exist, then one can try to think about some cluster structure on these varieties, and this is what we are trying to do. Okay, so we approach this problem by kind of posing another question. So let's ask the following question. Given a morphism B, given n by n non-degenerate matrix, can we restore A from which is compatible to B? So such that we will have this pair. A is unipotent upper triangular, and we require that BAB transpose is also unipotent upper triangular. We call it groupoid condition. And let's try to solve this groupoid condition. So let's just look at, for example, 2 by 2 matrices. Then B is just 2 by 2 general matrix. A is unipotent upper triangular, so it has such form. Then we can do simple computation, compute BAB transpose. And what we get is a matrix which has these diagonal coefficients. It doesn't matter what stays here, and something in lower left corner. Our condition claims that, well, first of all, we have to notice that this expression should be 0, and it dictates that A12 can be solved from that and has this expression. And then we can substitute this expression for A12 into this term and this term, and require to obtain ones. So since A12 is expressed in this way, so it implies that, well, first of all, our unipotent upper triangular matrix A is uniquely determined by 2 by 2 matrix B. Then substitution leads us to the following. Well, after we substitute and simplify, so we will get this element is equal to such expression minus B12 divided by B21 times determinant B. And here is another thing. And well, the system that the first coefficient is equal to 1 and the second is equal to 1 can be resolved if and only if determinant of B is equal to 1 and this ratio is equal to -1.
Is it a coincidence that it coincides with the condition for 2 Casimirs of GL2?
Great remark. Thank you, Andrei. Yeah, well, you steal my
very particular, yeah, it's some very particular set of Casimirs.
Exactly, yeah, it's important remark. Thank you. Yeah. So first, before commenting on your question, so let me just mention that for higher n, we obtain similar conditions also that determinant of B is equal to 1, and then if we kind of take block decomposition of matrix B in kind of such pieces that this is k by k piece and this is n minus k by n minus k piece. Then condition is that determinant of this piece divided by determinant of this piece is equal to -1 power n minus 1. And if both conditions, well, if the system of these conditions is satisfied, then there exists unique solution for matrix A. And yeah, exactly, Andrei mentioned this remark that this ratio is exactly a Casimir function for the standard trigonometric R matrix Poisson-Lie bracket on GLN. Well, all these long words, I don't want to comment on that. Well, probably everybody knows what they mean, so much better than I do, but just there is
Maybe trigonometric can be just kicked out because it's constant.
Yeah, well, it's redundant here. So, well, I prefer to kick out our metrics. Yeah, but anyway, so it's standard object for among Poisson brackets for GLN or SLN. Since we have conditions that determinant B is equal to 1, so we naturally restrict ourselves to SLN. So, and this is very well-known object in this theory. So now we consider a subset of matrices given by all these conditions, and we denote it by GLN circle, well, 0 above it. And well, corollary from what we said is that this subset is the symplectic leaf of the trigonometric Poisson-Lie bracket. So it's symplectic, like generic symplectic leaf of maximal dimension. Well, and also if we consider B from this symplectic leaf, then there exists unique solution for matrix A. So it determines the map phi from GLN 0 to direct product AN cross AN. No, sorry, not direct product, to direct product AN cross AN, square of pair of unipotent upper triangular matrices. Namely, for matrix B, we consider matrix A compatible with B and A tilde, matrix A tilde, which is a result of morphism B applied to A. So A tilde is equal to B, A, B transpose. Again, direct computation shows now kind of, again, going back to your question. So one can compute that if we equipped GLN, if we consider GLN 0 with the standard trigonometric Poisson-Lie bracket, then, and the set of pairs we equipped with direct product of Bondel-Poisson brackets, then this map is Poisson. Well, let's now consider particular case, restrict to the case n equal 3, and let's try to count dimensions. So first of all, what is the dimension of this space? For n equal 3, the GLN has dimension 9. Now, our conditions, as we saw here, we didn't see here, but it's easy to realize from what we discussed before that we have exactly 3 conditions on the metric. So totally this dimension of this space is 6. So 9 minus 3. And dimension of each an is 3. So 3 plus 3 is 6. So, however, matrices A and A tilde in this pair, they are not arbitrary. It's not like arbitrary pair. They must satisfy one relation. So let me explain this relation. Well, A is unipotent upper triangular, so one can write A in such form. And let's consider the following Markov function of matrix A. So it is 1/2 determinant A plus A transpose. By what we know, it is just Casimir of the corresponding Bondel-Poisson bracket, right? And it has the following. It can be expressed in coordinates x, y, z like this right-hand side. Let's compute M of A tilde, the value of Markov element for the matrix A tilde. So it's a determinant of B A B transpose plus B A B transpose one more time, so which is this guy. And we see that we can factor out determinant of B squared. So it's equal to determinant of B squared times MA. But B must satisfy conditions that determinant is equal to 1. So then, what we get that M of A tilde must be equal to M of A. Therefore, the dimension of the image of map phi is equal not 6, but 5. The image must satisfy one condition as a subset in the direct product.
Why is it
So
only,
this is how. Say it again.
why is it only one condition?
Yes, it's only one. It's one can check. Yeah, it's only one condition which is satisfied. Okay, so we have something 6-dimensional mapped to some 5-dimensional, and we know that our map is kind of Poisson. Now let's say, well, more or less the same thing what we discussed before, but in terms of some graphs, like using so-called Fogg-Gonchar parameter picture. Well, one can there is a whole theory of introducing coordinates on flat connection on the 2-dimensional surfaces, and one of the main part is the following construction. So let's draw such planar picture with this special graph. And this graph, inside triangle, this graph divides triangle into faces, and each face we equipped with one parameter. These parameters carries natural Poisson bracket, which given by the quiver, which is dual to this picture. So now we connect. We kind of draw another graph which is dual to that one. So vertices of this right graph are faces of the left graph, and we connect them by arrows in this way. Now, these arrows encode some Poisson structure, namely the Poisson bracket between parameters A and B, which are at the vertices, is equal to is equal to some constant times product A times B, where this constant counts. This should be omega. Counts the number of arrows from A to B minus the number of arrows from B to A. So, for example, in this picture, if you take Poisson bracket between A and B, then it is just product. It's 1, which is the number of arrows from A to B, times the product of A times B. Okay, what it has to do with matrices. So if we have such picture with this graph, so we can consider the we can construct unipotent, not unipotent, just upper triangular matrix in the following way. Let's label sources of the graph on the right side by 1, 2, 3, sources on the left side by 1, 2, 3, and we can consider paths connecting vertex on the left with some vertex on the right, like that. Oriented path going along the graph here. Then such path, any such path we equipped with a weight which is a product of all parameters staying above the path. Like, for example, for this red path here, so we consider the product of all these 4 parameters here. And we define transport matrix in the following way. The transport element of this transport matrix Tij is sum over path connecting J to I. Sorry, here must be I. Of sum of paths connecting J to I of weight of path. Then again, observation, simple one, is that this Poisson bracket that we discussed before, given by such a simple quiver, really induces the trigonometric Poisson-Lie bracket on these upper triangular matrices. It's very well known that Borel is a Poisson subvariety for trigonometric Poisson-Lie bracket. So this construction, basically, these parameters are nice coordinates for the corresponding Poisson-Lie bracket. They form log-canonical system of coordinates for Poisson-Lie bracket. So now let's modify this construction a little bit. So enhance it, like considering instead of 1 triangle, 2 triangles. So we can take 2 triangles. This one is exactly as the previous one. Here we modify directions a little bit, and then we join them together. This picture with parameters z here and q here, q alpha beta here and z alpha beta here, determine as collection of 6 matrices. So matrix T1, T1 bar, T1 tilde for this triangle. So T1 bar, it's kind of mapped from this side to that side. Sorry, T1 is mapped from this side to that side. T1 bar is mapped from this side to that side. And T1 tilde, it's here. And collection of 3 lower triangular matrices for the triangle directed, like pointing downwards. We denote these 3 matrices by T2, T2 bar, and T2 tilde. More explicitly, T1 looks like that in terms of parameters here, and T2 looks like some constant times such thing in terms of parameters here. And now we are ready to give solution of groupoid condition well, written in these parameters. Namely, well, first of all, we can notice that well, transport matrices T1, T1 bar, and T1 tilde satisfy these conditions, that if we kind of take some composition of like this one, and that one, well, with some reflection matrix S, which is given by that, then it will be identity, and similar thing happens for the second triangle. Also, kind of matrix form, Poisson bracket can be written in terms of matrices by such a matrix formulation. And so if we have such a picture, then we can consider the following product, which is given by this expression. So it's T1 inverse times S times T2 tilde times T1 tilde times T1 tilde transpose times S. And claim is that matrix A, which we obtain as such a product, is upper triangular. Well, it's pretty easy to see because, for example, here, T2 tilde is lower triangular, T1 tilde is upper triangular, but then you take transpose, which becomes lower triangular, so this product is lower triangular. When we conjugate by matrix S, we will get upper triangular, and product this with upper triangular give us upper triangular. And we also can write A hat as composition of, B is just composition T2, T1, where T1 and T2 are matrices which defined here. And A tilde, which is B transpose, can be kind of simplified as such expression. And it's also pretty easy to see that it is upper triangular by similar arguments. So, well, we notice that if we have picture like that, with these parameters, and we choose B like this thing, then solution of our problem, of our groupoid condition, is matrix A, which is given by such product, and the corresponding K tilde will be matrix given by such product. Now, let's try to interpret, well, make an interpretation for such products in terms of pictures. Kind of magnifying the picture, we will get again two triangles with T1 bar and T1 tilde for one triangle pointing up, and T2 bar and T2 tilde for triangle pointing down. Then matrix B is something like monodromy, some kind of transport matrix from this side to that one. It's obtained as composition of T1 following by T2. So T1 goes like this way and T2 goes this way. So kind of combining them, we will get path going like this way from this side to that one. Now, A correspond to sort of composition when we follow yellow path. So we start again from this side, go down, then somehow we jump from this side to top one and continue this way. So if you think about some kind of natural way to make this composition, we have to identify bottom kind of like bottom side with the top one, and then A correspond to something like this loop. And A tilde correspond to this loop up to the same identification. So when we can do this identification in the picture here, which means that we take two graphs like that, and then identify a top row here with a bottom row here. And this procedure is known in cluster algebra, and it's called amalgamation. And one can draw what is the quiver results after we do this amalgamation procedure. So now, what is the advantage of drawing these quivers and doing all this stuff? So advantage is the following, that it's very easy to understand Poisson structure in terms of these quivers. Really, quivers kind of encode Poisson structure. In particular, if you want to find Casimirs, it's very easy to find Casimirs in terms of this picture. I will skip details, but kind of one can easily write Casimirs of amalgamated quiver in terms of such objects. So, well, let's, for example, take this one and consider paths going this way with weights like 1, 2, 1, 1, 1, 1, 1, 1. It is closed path because this point is glued with that one. So, and the corresponding element here it's written C2 tilde, the corresponding element, it means that we take the product of all monomials in powers shown on kind of here. So it's power 1 for all vertices except this one, which is 2. Well, I will probably skip these details, but kind of point what I want to say is that it's very easy to write some expression, and in terms of this expression, one can find Casimirs of the corresponding Poisson bracket. So, namely, the Casimirs given, well, we found some expression, and Casimirs are exactly all this expression after amalgamations. And
Misha, may I interfere for a second?
Sure.
Yes, so just to mention that we have a transposition, and transposition actually inverts somehow a basis, so we don't have a oriented gluing.
And
that means that we have this, well, so to speak, strange identification. So we actually
thank you, Larry. Sort of. I forgot to mention then when I said that one can glue this side with that one. So this gluing should reverse orientation. So kind of this side going in this direction is glued to that side going in the opposite direction. Is it what you mentioned? So
yes.
If you consider this as a strip, so as a result of the gluing is sort of Möbius strip. It's not oriented surface, strangely. And we don't understand completely the meaning of this procedure, but it looks like it's some like for Goncharov construction introduce coordinates for flat connection on oriented surfaces. So what we do here is we introducing some coordinates for something which has geometric meaning on non-oriented surfaces, but we don't know exactly what the object is. Sorry. Yeah. Okay. So anyway, so bottom line of what what I told is that we can describe explicitly Casimirs and for this construction. And in particular, we know that, our groupoid condition can be resolved if some of these Casimirs are equal to 1. So in terms of these pictures, it means that we can consider the middle part of these pictures independent variables, and two sides, left and right, can be expressed in terms of all others such that this expression such that these conditions are satisfied. So, parameters which stay on this side and on this side are not relevant for us. They dependent on the parameters in the middle, so we can just get rid of them. So we stripped our picture from the left side and the right side, and the remaining side looks like that. So we have to take the previous picture, middle part, and identify top side with the bottom one, like gluing them in the opposite directions, like this direction should be glued to that. Result is a picture like that, and we are especially interested in the picture for n equal 3, which look like that. So this is the quiver which describe Poisson bracket for Goncharov parameters. And as we discussed, since we have map.
Mish, didn't you miss any arrow? You have
No. No, I didn't miss any arrow. So you mean this one, right? No, it's this is the right picture. Well, what happens here? So we take this middle part, right? Like this one. No, sorry, not this one. Kind of. Well, this line, it doesn't belong to the, and we identified this vertex with that one, and this. So what happens? So fundamental domain is kind of these 6 vertices. And you see that in the bottom rectangle, we don't have any arrow. We don't have diagonal arrow.
because of previous gluing.
Yeah, right. So really, this diagonal arrow in the bottom triangle is this one. So it just drawn in such way. The picture is symmetric, but kind of after identification, it stopped looking symmetric on how I drew it. Okay, so now the theory of cluster algebra can kick in, because we know that if we have some parameters which is described by quivers, then we can consider coordinate changes which sort of preserve Poisson structure.
Sorry again, you said that the dimension here is 6?
6, yes. Dimension is given by the number.
And what is the rank of Poisson bracket?
No, it's symplectic leaf. It is.
It has no Casimirs already.
It has no.
Yes, it's full dimensional.
It gives us parameterization of this guy, so which is symplectic leaf in for trigonometric R bracket. Well, but yeah. Okay, so now what I want to say is that so one can do cluster transformation with that one. There is a whole theory of these cluster algebras, but basically it says that one can do some kind of coordinate changes, nice coordinate changes, such that they respect Poisson bracket. In terms of quivers, like very briefly to mention, so it changes the quivers in the following 3 steps. So if you have quiver, so we can assign to each vertex of this quiver something which is called mutation at vertex k, at this vertex k. which is we change the quiver in the following 3 steps. So incoming and outgoing edges, for each incoming and outgoing edge to vertex k, it adds 1 extra arrow from from I to j here, like this one. Then it changes orientation for all incoming and outgoing arrows to vertex k, to the opposite ones. And then if after the first 2 steps we will obtain the pair of contra-oriented arrows, then we just remove this pair. It is how we do mutation. And then, as we noticed, vertices of our quiver are equipped with some functions, rational function, generally speaking, and they satisfy the following mutation rule. So, well, the pair xi, xk, xj, if we have that one, so it becomes the following, like we change xk to reciprocal one, and then we change all neighbors of xk by some prescribed rules. And this is just example. Again, I don't want to describe in details, just because I don't have much time to do that. Some very, very explicit and simple rules. So what we can observe in our situation, that like simple sequence of mutations transforms this quiver into such one or such one, which is really equivalent to quiver, which is pretty well known. It's called quiver X6. It's quiver pretty well known in the theory of cluster algebra. This is one of few cases when you do quiver mutations and you will get only finitely many quivers. There is classification of all such situations due to Pasha Felixson, Anne Felixson, Pasha Tumarkin, and myself. And this is one example of these quivers of finite mutation type. Okay, now let me switch gears and consider the second object in our picture. So this is Teichmüller space. We consider topological genus G surface with S holes. It's Teichmüller space parameterized hyperbolic structures, hyperbolic matrices on such topological surfaces. Or any such hyperbolic surface can be obtained by quotient of the upper half plane by discrete subgroup of PSL2R called Fuchsian group, and then description of hyperbolic surfaces is sort of equivalent to description of flat PSL2 connections. What else? Kind of general stuff. For example, one can introduce something which is called geodesic functions, namely with each loop on the surface, one can associate, like simple loop, one can associate its function on Teichmüller space. Namely, we just take monodromy, along this for this PSL2 connection, and take for this loop and take absolute value of the trace of the corresponding monodromy. This doesn't depend on the choice of representative. And this geodesic function can be expressed in terms of the hyperbolic length of the corresponding geodesic represented by this. Well, this space is equipped with a very famous Goldman-Poisson bracket introduced by probably by T. Abbott, but then kind of computed in more reasonable terms by Goldman. But for us, it's important that there exists very explicit construction which kind of make connection between Teichmüller space with one of surfaces with 1 or 2 holes of some genus and upper triangular matrices equipped with Bondel-Poisson bracket. So this construction is due to Leonid Chekhov and Volodya Fock. I don't remember what year, it was some kind of million years ago. Probably let me describe this construction on example. So, for example, our surface can be described by so-called ribbon graph for the case genus 1 and 1 whole. The ribbon graph is look like that. So as we see, we can think about that like having two vertical vertices and then considering three paths connecting these vertices. So each arc connecting the one vertex with another one is equipped with something which is called shear coordinate. We call them x1, x2, x3. And then geodesic function, these shear coordinates are log-canonical with respect to, they satisfy the Goldman-Poisson bracket written in terms of the shear coordinates looks like that. You see, it's again, shear coordinates again form log-canonical system for Goldman-Poisson bracket. And geodesic functions written in terms of these shear coordinates look like that, like with square roots, some expression with square roots. And now we can do the following. So we can make a map from such picture for three weights, x1, x2, x3, to 3x3 upper triangular matrix with three parameters. Namely, we consider three special simple loops. One is like that, another one is like that, and the third one is like that. It is, we can, in a clear way, we can denote them G12, G13, G23. So G12 is the loop which is obtained by sort of concatenations of the arc 1 and with arc 2 here. And Volodya and Lenya proved that this map is Poisson map, where the left side is equipped with a Bondel bracket, with Goldman bracket, and this one is equipped with Bondel bracket. So, for example, in this picture, so the Poisson bracket of element G12 and G13 is given by the following expression, and then we have to use like cyclic permutation to write all other two remaining brackets. Okay, probably let me skip that. Now, let us try to make connection of this Teichmüller picture with the previous pictures that we discussed before. So let's consider Markov element for our 3x3 matrix. So, which has the following expression in matrix elements. Geometric meaning of this Markov element is the following. So it is, if Markov element is fixed, it means that the length of this loop going around the boundary, our surface is genus 1 curve, is a torus with one hole, right? So if you consider boundary of the hole, it should be geodesic, and the fixing Markov elements fix the length of this geodesic loop. So the picture that we get is the following. And we know that now, let's consider, remember that we have our map from the previous case. So here we have map phi from matrices B to where B is from GL3 naught to pair of matrices A and A tilde. This map has one-dimensional fiber, right? So A is unipotent upper triangular, so it corresponds to one torus with one hole. And A tilde corresponds to another torus also with one hole. Condition that we also describe that the corresponding Markov element for A coincides with the Markov element for A tilde in the image. Right, so if we translate it using this remark, so it means that the length of the hole coincides with the length of the second hole. So we can glue these two tori together in one genus 2 surface. Note that gluing introduces, well, the dimension of this hyperbolic surface is free, dimension of this hyperbolic surface is free, but they must satisfy one condition, that the length of the hole must coincide. So the total dimension of two things with conditions that length of the hole coincide is 5. However, gluing introduces one extra parameter, because when you glue two things, you can rotate the top one with respect to the bottom one, right? So, and the idea is that here on the left side, we have 6 parameters. And these 6 parameters exactly parameterize the surface which we obtain after gluing. And well, the claim that I want to tell, I don't have time to do it but properly, but it's exactly the case. So kind of main idea is that it's exactly the case. And this means that these parameters give us nice, in particular, it provides us with nice coordinate, which behaves nicely with respect to the Goldman-Poisson bracket on the closed genus 2 surfaces. Now, moreover, so this parameters A, B, C, D, E, F has cluster meaning, so one can do cluster transformation, cluster mutation with them. And in particular, one can write all geodesic functions in terms of all these parameters, which give us some kind of very specific expression for geodesic functions. And kind of also one can express dent twists as sort of combination of cluster mutations and then some symmetries. Symmetries means that permutation of vertices and corresponding quiver. So we got some sort of cluster algebra formulas for expressing dent twist in the corresponding Teichmüller spaces. I will probably skip that because I really don't have time. So let me just say that main corollary of what we all discussed, that it's the following. Yeah, probably to make it more clear, so I have to add one tiny remark that when I said that all dent twist has expression, nice cluster expression, it is true for some dent twist when we consider quiver x6, but not for all of them. So if we want to consider dent twist around this loop, then the corresponding transformation doesn't have cluster form. However, we can make it cluster. So we have to add one extra vertex to our quiver x6, transforming it into such symmetric quiver, which is also has this mutation finite property, and it's called x7. But we have to pay the price for that, introducing this condition that well, this expression is a Casimir for this quiver, and we need to make this Casimir equal to 1. So in order that well, to write the correct formulas. So bottom line is the following: that this coordinate ring of Teichmüller space of genus 2 curve, closed genus 2 curves, is isomorphic to variety obtained by conditions that Casimir is equal 1 into cluster algebra associated with this quiver x7. And probably let me stop here because, yeah, I'm run out of time. So this is the main message that I want to say. Thank you.
Are there any questions? Okay, if there are no questions, let us thank the speaker again.